Jon-Fredrik Nielsen is a research associate professor in the fMRI laboratory at University of Michigan, specializing in MRI sequence design and implementation. He created and manages the Pulseq interpreter for General Electric scanners and is co-PI of the Harmonized MRI project that seeks to implement and disseminate vendor-agnostic functional and quantitative neuroimaging protocols for more reproducible MRI research. Thanks.
Okay, great. Hope you can see my screen.
Yeah,
So
perfectly.
great. So thanks so much. This is a really great workshop, and I'm really super happy to support, open science. So we're a team of MRI pulse programmers, MRI physicists, as they would call us in radiology. And we've developed a tool for harmonizing MRI pulse sequences, or the acquisition side of things. And I'll talk about a little bit about what this is, and the history of how it came together, and a little bit about the strategy of how we obtain our funding, and some recommendations. So I'll talk about what Pulseq is, and then I'll talk about how to sustain it, and then it has kind of three components, or several components to it. So here's kind of the big picture as I see it. So you're here in the middle. You're a scientist, or an MRI physicist, a developer, and you'd like to implement your pulse sequence using Pulseq, and you'd like to, get funding or interact with all the stakeholders that might benefit from this, or that you might benefit from. And so, of course, you're part of the research community, and so you definitely rely on them. At the same time, the field of MRI is driven by the vendors. They provide the hardware for us, and largely the software. And then there's the funding agency. And so there is a significant amount of overlap and synergy here that I think we can benefit from. And so I want to try to explain our philosophy and where we see ourselves, and hopefully that'll be useful to some of you. So some of the slides here are taken from an ISMRM virtual meeting that we held last year in November. It was about Pulseq, and it was great. It was 3 days of talks, and all the talks are available as PDFs on this website. So what is Pulseq? So Pulseq is actually several things. So it's a language to describe MR pulse sequences, and it's also the software to generate such pulse sequences. And pulse sequences are fixed successions of RF and gradient pulses and ADC events. And Pulseq scripts, they can regenerate Pulseq sequences to accommodate user input. So it's essentially an ecosystem that includes sequences and the software to generate them, and software and hardware to consume them. So that's perhaps a little bit vague, but it's essentially many things. So the idea of, or underlying philosophy of Pulseq, is to minimize the effort that the pulse programmer has to make to implement and support their sequences, and to remove that initial threshold, and to make researcher-oriented features more easily accessible, and to prevent typical sources of human error. And in general, to promote a kind of open source thinking for sharing and exchange. And this is in contrast with the software that the vendor typically provides for programming sequences. So here's an example of an MRI pulse sequence. And this also demonstrates how Pulseq defines or represents a sequence. So the key here is that Pulseq views a pulse sequence as a concatenation of non-overlapping blocks. So each block here is indicated by these boundaries, the red dashed lines. And you'll have an RF waveform and one or more gradient waveforms in each block. So that's basically as simple as these sequences are. And so it should be possible to describe these using an open standard, and also provide tools for designing them, for plotting them, and then putting them on the hardware. So that's the main idea of this project. And so to do that, we provide some high-level programming environments. So there are at least a couple to choose from, or several to choose from. So the quote-unquote official toolbox is still written in MATLAB, but typically all the actual scripts and sequences are still open source. So this still has a very strong open source flavor to it. There's a Python version of the Pulseq MATLAB toolbox that's called PyPulseq. That's fully open source. It tries to implement the same features as the original toolbox and tries to keep up with that. There are other tools that can export Pulseq files, such as GammaStar, which is another environment for vendor-neutral imaging, pulse programming, and simulators such as GEMRIS and Core MRI. And so here's what a Pulseq script might look like. So you start out by defining the hardware system properties. So this particular example is a MATLAB script, but it could be a Pulseq script. You then describe the sequence parameters, and then if you like, you can use this built-in functions, helper functions, for creating RF pulses and gradients. So this mixing pulse would then create an RF event and a gradient event, or you could create these by hand if you like. And there are other helper functions as well for creating shapes and events that are used frequently in MRI, such as trapezoids and data acquisition events. And basically then in the scan loop here, you would add these blocks one by one. So in this example, you add an RF excitation pulse and a gradient, and then some imaging pulses, and then a data readout event. And this is essentially the entire script that you would need to implement a 2D gradient echo MRI pulse sequence. So you can see that there's nothing vendor dependent here. It's all done using intuitive function calls, and you also have access to all of these events. So this add block function will add the block to the sequence, but these events are just simple structs that you can look at and you can modify by hand if you like. So it's a very simple and straightforward way to represent sequences. And the key idea here is that once you have this file, so you write this representation to a file, you can copy that to the scanner and run it. And we can do this on multiple scanner platforms. And this guarantees identical execution of that sequence on different platforms. And that's not possible using the vendor-provided whole sequence development tools. So that's the underlying technology here. And just to give you a little bit sense of sort of the level of detail that we operate at. So this is what you can do with Pulseq. You can specify exactly the start times in microseconds for each of the gradient waveforms and the stop time. And you have full control over essentially the hardware at the same precision that built-in sequences do. And so just a little bit about how I got involved with this. So the Pulseq itself was developed by another group, University of Freiburg in Germany. And I tinkered around. I built a tool that's a lot like Pulseq conceptually that I called Toppy for my own use for a particular vendor, for GE, that I needed to essentially rapidly try out new pulse sequences for my own use. And then at an ISMRAM conference, I met the first author of that Pulseq framework, and we realized that we were essentially solving the same problem, just using two different approaches, and the file formats are basically compatible because one representation can be transferred to the other and vice versa. So then the idea seemed pretty obvious to us that we could use my Toppy interpreter as a Pulseq interpreter. And that's exactly what we did in the original Pulseq paper. So it was somewhat serendipitous, but it was an example, I think, of building tools that you find useful. And then, when you do that, you don't always foresee what it might be useful for, or what it might become later. So that was really, really fun to realize. And since then, we've spent a lot of time I've spent a lot of time refining the interpreter, keeping up with updates to Pulseq, and making a more robust and accurate interpreter for Pulseq, and more native interpreter. Also to support various users. So that's been a lot of fun. Around 2020, we got NIH funding that I'll talk a little bit more about. And that was for functional MRI, and also involved with a related project for developing Pulseq sequences for neuroimaging, other neuroimaging applications. And we want to keep going. We want to expand the utility and the possible use cases of this, such as making the user experience more interactive, and perhaps also add some online recon options. So those are just some of the things that we're heading towards. This is all still very much research driven tool, but we are starting to see significant uptake. This is just a brief example of, this is what my framework looked like. There was actually a collection of different files that defined kind of each block, if you will. And so it wasn't quite as, it was a different sequence representation, but we were able to port them to Pulseq, to and from Pulseq. So that's the idea. And here's just an example for those of you who know functional MRI. You might recognize this as a so-called simultaneous multi-slice EPI sequence with a RF excitation gradients here, RF excitation pulses, and then an EPI readout. And the point is here to simply show that we can take a Pulseq file, implement it, and play it out on the GE's simulator in this case. We can get an accurate translation of the Pulseq file. These are just a few examples of some of the things that users have done with this. So, for example, for demonstrating improved reproducibility in diffusion MRI or quantitative imaging. So that's Pulseq. So the main idea is to define the pulse sequence in a way that can be played out exactly the same on different vendors. And so the question that's more relevant here is how to sustain it. And as I see it, they're kind of, the first thing to point out is that the file standard itself, so you want to think about the Pulseq file standard, which is essentially the core of Pulseq. You can essentially reduce it to just that. So Pulseq is a file standard. It's a standard representation of a pulse sequence. That is done. That's free. We don't need funding for that. What we do need to sustain our development of the design tools and the interpreters. So right now there exist interpreters for at least the three largest human vendors, and I believe also other vendors are actually coming on board pretty quickly. And those are being developed by both the research user community and actually now the vendors themselves. And so maintaining these and finding funding for those, that's really where the need is. So again, the idea here is various design tools can be used to generate a Pulseq file, and then interpreter, then you would then need a vendor-specific interpreter to play that out on a particular scan. Actually, in principle, a lot of these tools could still be closed source. Of course, we prefer open source because it's transparent and we can guarantee, quality and such. But in principle, Pulseq is sort of agnostic to whether some of those tools are developed or maintained in a closed or open source kind of environment. So what's needed to sustain this? So I think there are several aspects to this. So we want to maintain the interpreters and design tools, and that takes developer time for a few, sort of the core development team. We need the vendors. We need vendor support, and that's essentially free in the sense that what we really just need there is, grant letters of support and access to system information. We need that information. We need their programming tools. We need to know if their systems need to change and so forth. The other thing that I think is important for sustainability is community uptake, and this has kind of several facets to it. One is, we need the developer team needs to provide documentation for training, and then also support users, and they will provide bug reports and feedback, and that requires a significant investment in time. And then the key to really get this off the ground is then to demonstrate utility for specific applications. So I'll just talk briefly about these. So for the interpreters and design tools, yeah, as I said, they're mostly community developed at the moment, but actually we think, seeing vendors actually starting to provide tools as well. We don't have direct funding for supporting the infrastructure itself. I think as far as NIH, which is the main funding agency that we look for, at least in our field, is NIH. So the possible funding sources there that I'm aware of are essentially administrative supplements to support software tools for open science. And there's now a new mechanism that I think would be very interesting for us, and that's the RO3 mechanism, Building Sustainable Software Tools for Open Science. So I think that's something that we all should be looking at and try to collaborate on. But I would say that even with that, so far options for direct funding for software development from NIH is perhaps more limited than the regular funding avenues. So just a bit of a word about vendors. I'll try to keep this brief to keep us on time. So I think vendors do have incentives to support open pulse sequence, vendor neutral pulse sequence development. One is that they want to support research and development because that can benefit them, but they also, they're people. They want to see this field thrive. I think they see benefit in prototyping new methods. So both for research collaborators and perhaps also internally. They also want to make sure that the Pulseq interpreter represents their hardware fairly, so that it makes full use of the system capability. So they have an interest in providing information to the interpreter developers to make sure that the full capabilities are used. And then there's a little bit of fear of missing out, I think. They want to keep up with other vendors, which is actually a good thing. So I think this is a case where the community really is pulling this along and taking the vendors, kind of pulling the vendors along, which I think is healthy. Of course, there are disincentives. I think really the main one I can think of is there's, I think, potential here for reduced demand for proprietary protocols. So I think that's that's something that we have to perhaps acknowledge and be sensitive to. But I think it's, I think we should be aware of it. But at the same time, I think there's enough synergy here overall to be able to find some common ground here. And there's significant benefits here to the research community. As I said, the access to system information, especially for safety checks, and also for research, vendors can be an avenue for connecting with other research users because they collaborate with other researchers, and if they need your tools, then and we're seeing that, then they'll put you in touch. So it's actually been quite rewarding, even just for pure research networking from that viewpoint. And they also provide feedback on features and needs, and we're also benefited from that, and that's helping to guide our actual open source development as well. And then the community uptake, that really has, a couple of components: user training and support, and then applications. And so community is really where the energy for all of this lies, and that's really the alpha and omega of this. It really is. Open source development is, I think, key in the long run to really provide the scientific benefits of this and to really realize the full potential. For transparency, bug fixes, performance guarantees to know that the interpreters really are accurate, so we can peek inside and know exactly what it's doing. And also to guarantee that this is going to continue on in the future, so that if the vendor manages a tool, then they could they could perhaps pull the plug or stop to support it. And I would also point out that I think one thing that's benefited me a lot, and that I would really stress, is also to think about open-minded development. And to me, that really means being willing to give up your own contribution in favor of evolving consensus. And then, in my case, it really means it meant giving up, what I call TOPI, or sort of that framework. It was doing the same job, and perhaps was more tailored to the particular vendor that I was on, but it wasn't really serving the broader community. So I think that's something to keep in mind, that it's okay to move the field forward a little bit. If you made a contribution that was useful for a while, you should be proud of it, but also be ready to join forces if that's what will benefit the field the most. And really, for funding, to really get to that, I think the key here is really to focus on the utility for applications. And this is probably perhaps biased toward NIH, that it really needs to see some scientific or application benefit of this. And I think really the key here is reproducibility. So this is where open science and open source science really shines and can really make a difference. So open science provides transparency in the experimental conditions. They're known and they're well documented. And something like Pulseq, where you document the pulse sequence exactly down to microsecond precision, is totally needed. Right? And before Pulseq, it was almost impossible to communicate exactly what the MRI experiment was. I mean, the best you could do is, you could draw a chart or a graph in a sequence timing diagram in a journal article, and that was about the closest you got to what was actually being played out. There are lots of details that really should be documented well, and with Pulseq, it's all there. And also, open source tools guarantee that the tool will continue, and also that it's well performing. And so we chose to focus on functional MRI, and I will just briefly explain that in 30 seconds. And then I'll also say that going forward, I think quantitative MRI is really a perfect match for open science and for this kind of framework. I'll skip this. So essentially, the science pitch that we had to make to get this funded was there's variance in functional MRI measurements, or in MRI measurements in general. And there's this site variance that we don't really understand, but it has many sources. If you look under the hood, there's the pulse sequence, there's calibration scans that you run, and you acquire the data, you reconstruct images, and you pre-process. And each of those steps can impact image quality and the variance. And what we're trying to do here, instead of the current practice, which is leave it to vendor, it's all in a black box, we open up that black box and make all the software components vendor agnostic and open source. So we're actually able to do this because we can control the acquisition, and then we also have a uniform image reconstruction. So that's the idea. And so we were able to get a U24 grant from NIH to focus on functional MRI, and also part of an R01 that focuses on other neuroimaging applications. But this is all focusing on reproducibility. So I would stress that it's about reproducibility, it's about open research, it's about objective quantitative measurements that across multi-sites. So that's really the pitch that I think we have to go for, and that the NIH would respond to. So I'll just leave you with acknowledgement. This is a little bit biased toward the vendor that I'm at, but these are the key folks who have contributed to this project. All right, thank you very much.